so I guess let's kick this off. My name is Erik Osheim, and I am coming to you from Providence, Rhode Island. I work for a company called Meetup. A few of you might have used our service for like programming meetups and things like that. We're based in New York. We are also hiring Scala developers as well as Java, JavaScript, Python. We're sort of a polyglot place, so if you are interested in being in New York or the East Coast, definitely look me up. Before we get started, I just want to do something a little bit non-standard here, which is I'd like to take questions during the presentation, and the reason for that is that this is sort of a weird topic, and I don't really want to lose people, so I'd rather, if someone has a question about something, I'd rather hit it at that moment rather than having someone wait 30 minutes to ask a question about my third slide or something, and they're going to have a harder time getting something out of this talk. So I don't know if that's okay format-wise, but I'm just going to, if you have a question, just raise your hand or something, and I'll try and stop and call on you. All right. So the purpose of this talk is basically generating implementations. I'm just going to leave that general here from anonymous functions. So the technique uses macros. Specifically, it's now using quasi-quotes. And the technique is mainly for optimization purposes. We're not doing this to sort of express things that were previously hard to express, but rather we're trying to do it to get sort of the bytecode that we want for whatever reason. This is sort of a work in progress. It's not something Meetup is doing in production yet. It's a thing that sort of personal interest of mine. So, take this as far as it goes. And sort of on this note, I think it's worth diverting for a minute. I mean, I think Paul's talk sort of looms large here for me. And I think he sort of rightly criticizes a lot of fundamental problems in Scala and sort of says, how can you build on this foundation when it's sort of a ball of mud or a lake of mud or a sea of mud or whatever mud geologic sort of structure there. And I think it's a totally fair point. And there's a way in which maybe this talk or these sorts of experiments are sort of like playing the violin while the city's on fire. I mean, it's true that I'm sort of mutating the language to add these extra capabilities, which is maybe not the thing that Scala, the language at large, needs the most. And it sort of felt bad for a while, but I mean, thinking about it, I guess you can think of this either as a justification or as a post hoc rationalization. I mean, either way, but is that I think as the JavaScript communities, other communities have shown us, we can sometimes do interesting things even when the foundations are weird. And so in this case, maybe I'm not building a tower on a lake of mud, but I'm building a pontoon or a raft or something. And and if I'm really successful at building a raft, maybe we can build a raft city and and then build towers in our raft city. And I mean, who knows, right? I mean, I think it's a fair point that like the language is evolving and that while it's true that it's hard to communicate with a random Scala developer, you don't know. I think once if a group of people agree on sort of a dialect, if you will, or a subset or a different strategies, I think we can still have productive dialogue, share libraries, share code, and do what we need to do in an interesting way. So this talk is really about macros allowing us to expand the language in this way. Whether it's a good idea or not is sort of up for you to decide. So just really quickly, how many of you have used macros or feel like you have a good handle on what macros are? I guess raise your hands. So maybe like a fifth of you or 6 of you. Okay, that's totally fine. So just really quickly, these aren't like C macros where you're taking a string as program text and building a new string. They're a little more principled than that. We're basically, at compile time, we have these parse trees that are typed, and we can write functions that operate on those trees and build new trees, and the types are enforced. So you're not going to have this problem of like a macro totally changing the meaning of your program. Or maybe you will, but only as long as the types are the same. As I say, functions from ASTs to ASTs. Anonymous functions, I mean, I think this is something people probably know, but by anonymous function, I mean this sort of syntactic structure where the functions, the functions like body is literally right there, x to x plus 6, that's it, that's the function. And I've written it 3 different ways just to show you sort of the variety of anonymous function syntax. The last one down here isn't really what I mean. I mean, it technically is an anonymous function, but it's really just an anonymous function wrapping a non-anonymous method. So the work is actually happening over here in +6, and our anonymous function is really just an anonymous function applying +6. So this is not the case that I'm focusing on here. And inlining, again, I think people probably know this, but by inlining I really just mean rewriting a function application or possibly a bunch of function applications with the implementation and doing some rewriting to get the same effect there. So in this example, we've got a bunch of methods sort of that are kind of calling each other in a nested way. And when I do the inlining, what I really mean is I just want their implementations directly on each other, as if you'd written it as one function, not as 3 or 4 or whatever. And for those of you who've been working in Java a lot, you sort of have a sense that the JVM's probably already doing this for you, and it totally is. I mean, inlining is a very important JVM optimization technique. And so if you sort of read the documentation, one of the big things that this inlining buys you when the JVM does it is it increases what it calls the horizon of optimization. In other words, the compiler has a sense of what's happening in this particular region, and as you grow that region by inlining, if it can be sure that there aren't side effects or other things happening, it enables bounds check elimination, potentially certain kinds of loop unrolling, optimization of use of local variables. There's lots of cool stuff that can be done. And on the JVM, static, private, and final calls, in other words, those that can't really be overridden, are easy to inline. You can be sure that you're inlining the right thing. Other calls, maybe you inline, maybe you don't. The JVM often will optimistically inline methods that might not really be safe, and we can sort of go into what that means a little bit more later. But those optimistic inlining calls will be de-optimized later if necessary. And the reason you would need to de-optimize is if you have a bunch of different implementations of this one method in different subclasses. If you've written some code in terms of this interface here, the interface in my hand, you might inline, if you only ever have one subclass, you might just inline that subclass's method here. So when you see the method called to the interface method, you know that, oh, that's always going to be here. And so you can just go directly to that method. But the problem is if we have a whole bunch of different subclasses, you have to use a V table or something like that where you say, okay, well, which type do I really have? And which method should I use for this type? And it has to go through the inheritance hierarchy and sort of figure all that information out. And that's fast. I mean, it's not super slow like hitting the database, but I mean, there is a cost to it. And those types of calls are called megamorphic calls, as opposed to monomorphic being the case where there's only one subclass of this interface, and bimorphic being the case where there's two. And those are cases that can be optimized. How many of you have heard of the inlining problem? All right, so I guess Alex. Great. So Cliff Click, who's sort of an important JVM person, worked on JVM implementations, basically coined the term in 2011 to describe this problem that he was seeing. I mean, I think he talks about it in the context of JRuby, but lots of situations have this. And basically, it's a situation where, due to writing things in a functional style, you lose JVM optimizations. And Cliff Click talks about this as losing a 10 times program speed up. So your program is 10 times slower than it would have been if you hadn't written your code a certain way. And here's sort of a translation of what he's talking about to Scala. So basically, this is just a really simple class. It's maybe reminiscent of a less functional version of Stephen's class, right? So we're blitting some arrays of ints. We've got a blitting function here, which is the way we're combining our pixels. And we've got our two source arrays, two source rasters, and we're producing our destination raster, and we're essentially just looping through doing the work. This is obviously mutating the dest variable. It's horrible. Stephen's thing is way better, but this is the way Cliff Click sort of frames the problem. And the point that Cliff makes is that actually this iteration logic may be complicated. This may be tiled. It may not just be one loop. It may be nested. There may be parallel computation going on with fork join. There's all sorts of things that could be happening that don't have to do with the essence of the operation. In other words, adding 2 pixels or masking or whatever sort of pixel operation you're doing, but instead have to do with the sort of details of our image library. And so basically, the fact that we've abstracted out f means that if, let's say that we build a bunch of different blitters, one that adds pixels, one that subtracts them, one that masks them, that's going to be a megamorphic call like I previously described. There's 3 different anonymous functions. There are going to be 3 different classes with 3 different versions of apply, and it's going to be a megamorphic call site. It can't be inlined at this point. So I feel like if you haven't seen this problem before and I'm telling you this, now you're probably freaking out a little bit where you're saying, well, I use map, I use exists for all flat map. I use all these methods that use exactly this pattern. Does that mean that my code is 10 times slower than it would be? That's terrible. How can this happen? And I guess, and how can we fix this? Is it really a problem? How can we fix it? And what should we do? And I would say that the paper was written in 2011. It's 2013 now. My own testing, I haven't been able to find a case where it was 10 times slower. I was trying, before this talk, I was doing a bunch of different benchmarking, and I've mostly observed a two times slowdown I was able to construct a case that had a 5 times slowdown, but it's a little bit artificial. I don't think it's really a 10 times slowdown in most cases. And it's only observable in megamorphic situations. So if you're going to write micro benchmarks to test this for yourself, you have to be very careful, because if you have a bunch of subclasses but you only use one of them in your benchmark, the JVM will happily optimize that case. So you need to be a little bit careful. I mean, like most micro benchmarking. And a lot of programs, if your anonymous function takes a long time to work, then this cost won't matter at all. In other words, this is only important when the inline function is very small. So things aren't quite as bad as Click says. And you won't probably get a 10 times speed up if we fix his problem. So is it even worth talking about? I mean, and I would say yes in some cases. I mean, I think raster processing is an example where I think you can get benefits. And in a past life, I worked on raster processing problem where I would have liked to use this technology I'm going to show you. So I think there's cases where it matters. If you've ever said the phrase manual specialization, I think this is definitely a technique you're going to want to use. Mostly, if you're affected by this, you probably already know it. And if you aren't experiencing this problem, then maybe it's not a problem. But I find it interesting, so let's just check it out. Darn it. Great, so using macros to inline in functions, what do I mean? I want to write a method that can accept a literal function, but then rewrite its own call to just use that function immediately, as if you'd written the literal code. So if you look here, at the top we have a normal method call. I pass it an f, which is a function, and an n, which is an int, and it's going to do the thing you expect. It's going to call f of n on 6, which will then evaluate 6 times 3. At the bottom is sort of what I want to happen. There's this secret method, which I'm not showing you how I implement it. But what I want to happen is if I pass it secret 6 and then an anonymous function multiplies by 3, I want that to be as if I'd written 6 times 3 in the code myself. I don't want there to be a method call. I don't want there to be anything else. I want it to be a little bit more like a C++ macro or a C macro in a sense, if you're familiar with that. Out of curiosity, how many of you have used like Lisp macros? So maybe a few people. How many of you have used like C macros or C++ macros? Okay, great. So a lot of people, so you have an intuition of kind of what I want. I want this to behave in this case a little more like a C macro and less like a method call. And the reason the function has to be anonymous, I sort of touched on this, but just to review, is that if you pass me this bottom thing tripled here, you're handing me a function, and I can see that it calls tripled, but I don't actually know what tripled does. I can't inline the implementation, and that has to do with the way the Scala compiler works. I mean, that's just a detail, but it's a very important detail. If you give me an anonymous function, I can look at all of its guts, and I can see everything that it does. If you give me an anonymous function that just calls a method, all I can do is call that method. I have nothing else I can really do. That's why I talk about anonymous function literals. Any questions so far? Is this making sense to people? All right, great. Let's keep going. So what does a macro look like? Well, there's basically 2 parts to a macro. There's sort of like the part that if you're writing a macro as a library author, there's the part that your users see, and then there's the part that you sort of sweat blood on. And the top part is what your users see, the secret method here. And the bottom part is the part that you have to write. And I haven't written the implementation yet, but you can see the types. And these obviously are related. If you look at them, you can see that the bottom one has this weird context parameter list, and then but then after that, it has the same sort of structure as the top, only instead of an int and a function from int to int, we have these exprs. We have c.expr of int and c.expr of int to int, and those are essentially ASTs. Those are coming from the Scala compiler, and that says this is some sort of expression. It could be arbitrarily nested. It could have all sorts of stuff going on, but it returns an int. So that's all you need to know, is that this is a tree, and it returns an int. And then f, it's a tree that returns a function from int to int. And so this is sort of a rough approximation of what the tree looks like if you actually like print it out and look at it. So that scope.secret call becomes this whole bottom thing. This is sort of like an expanded tree. And it's even a little bit simplified. But if you take a minute, you can sort of see that apply means call a function. So, and the first argument there is the function we want to call. So we select, we grab the secret method out of scope. That's what that select line means. And then that list is the arguments we're passing secret. And there's 2 of them. There's a literal constant 6, which is the first argument. And then there's this whole big tree here, which is that function. That's the anonymous function. That's the anonymous function literal. And it tells us it takes a parameter called x. That's the first thing, list there. and it applies that subtree, which is calling the plus method on list and passing the constant 3. I guess actually I use plus instead of star here. That should be a star. I obviously screwed this up, but you get the sense, right? I mean, it's the same idea. And there's a little bit more complexity because I actually simplified the tree. There's these horrible name things you have to work with too. So it's actually new type name and new term name. But if you go back, you can see the places where I talk about scope, scope and secret. That's what would really look like. But I thought it sort of cleared it up to move these to 2 different slides. So for doing an inlining transformation here, what I want to do is take those trees that you saw, take that whole tree and produce a new tree. And that new tree should be as if you wrote the code that you wanted to write, the 6 times 3, the simple code, as opposed to this whole method call. And so I need to do sort of 5 steps. I need to verify the arguments are valid. And in this case, what I really mean is you need to have passed me a function literal, anonymous function literal. If you didn't, then it defeats the whole purpose, and I'm going to issue a compile error. You could also issue a compile warning and do something else. I choose to make it an error for now. Then I actually build the result tree that I want, or I start building it. After that, based on that tree that I built, I inline the anonymous function. I inline the arguments, which is sort of completing the inlining, the step, and then I do a little bit of cleanup at the end. So this all is sort of could be thought of as one big inlining, but I'm sort of breaking it out into the different steps so we can talk about them. Geez, this is... All right, can everyone, well, shit. Okay, that last word there is literal, sorry. Anyway, so this is sort of like in pseudocode, these are the steps I'm gonna do. The top is what the user would write. So they're assigning to Z the result of this secret call where they pass those 2 things. So the next line is sort of where I'm going to actually apply that function. This is before inlining has happened. So the second line shows you if I take that anonymous function and immediately apply the value 6, I'm no longer calling scope.secret. I've removed that method call, but I'm still building an anonymous function and calling it, which I don't actually want to do. So in the third line, I actually go ahead and just inline the anonymous function's implementation. And that third line, as you can see, is not actually valid. There's no X in scope. This is sort of temporarily. I've inlined that, and now for the fourth line, I take 6, which is my parameter for X, and substitute it for X. And after this whole step, I've now got what I want. Val Z equals 6 times 3. It's a dumb point, but if any of you have done stuff with the lambda calculus, this is a little bit reminiscent of beta reduction. I don't have like, what is it, Ada. This is only the beta reduction part. So by itself, I don't think it is, but I'm going to be silent on that topic. And in case you think this 6.3 example is really dumb, I just chose something really simple so we could fit it on slides. I mean, this could be an arbitrarily complicated anonymous function. It could be doing tons of work, and it would still work the same. This is just a very simple example to sort of show you how it's done. And so you might ask, how do you build that tree? Because that data structure we saw is horrible. And building one of those things by hand would be, oh, question. So that's a great question. The answer is I'm going to be inlining whatever the user passed as 6. So as long as I inline that once, it's okay, but you're right. If there were side effects for 6, that could be a huge problem. And so I think the answer here is that, and this is a point I'll come back to later, but you have to be clear for your users, when stuff's being inlined, it needs to either be side effect free or they really need to know what they're doing because, yeah, side effects are going to ruin your day. And that's just... I'm not really going to do anything like check to see if there are side effects. I think that's a losing game anyway. I think that this is intended to be used in mostly a pure style, and if you don't, it's sort of on you, really. So as far as building these trees go, I showed you that tree, and it's really horrible. The nice thing is that there's actually a really cool compiler plugin that you can use to help you build trees. And it uses the string interpolation syntax that was introduced in 2.10 to do something really nifty. So imagine that I have those expressions. I have n, which is an expression for an int, and I have f, which is an expression for a function from int to int. And I want to create that method call. That next line is all I have to do using the Macro Paradise plugin. I basically say q for quasi-quote. I'm going to use triple quotes here just so that if I had new lines or something, that would be fine. And then I'm just going to say $f to interpolate the function tree. I'm going to call the apply method on that, and I'm going to pass in $n as the parameter. And this will totally create a valid tree that takes a function f and calls it with a value n. This is before inlining happens. This is just producing some valid Scala that I might later want to inline. So now we want to do the actual AST transformations. And so this is the sort of, at a high level, this is what we're doing. We're going to build this thing called a transformer, and that basically just involves implementing this transform method. The transform method does one thing. It takes a tree and it returns a tree. And it can do whatever it wants as long as it does that. In our case, the way most of these get structured, and the way ours is structured too, is that you look at the tree you're given and you look for certain features. So in our case, there's two different trees we need to match. The top case is where you literally call apply on a function. So it's like a function dot apply, like I just in my last slide. And the next one is where you implicitly call apply by just putting parens. So it's a function, open paren, the arguments. And as you can see, those trees are very similar, but they are different. There's a select node in there, and that will ruin your day if you only handle one of those cases. And so in those two cases, I want to build a new tree. I want to do inlining. That's the whole point of this talk. In every other case, I do whatever the default transform behavior is, which in this case is recursing through the subtrees here. So I get given a tree, I see if it matches what I want to handle. If not, I let the transformer keep doing its thing, and it'll just recursively descend through the entire tree, trying to match subtrees against this thing that I provide. So this is the way most of these kinds of rewrites you'll do will look, if you choose to do them. So we'll just handle one of these cases, the smaller ones. It fits on slides a little better. And this is, at a sort of high level, all that we have to do this inlining I'm talking about, which is basically that we take the params that the function expects and the arguments that we were given, and we zip them together. So we say, you know, if you expected two params, x and y, and you were given 3 and 6, we zip 3 with x and 6 with y. So now we have tuples that show the variable bindings for this function call, right? That's pretty straightforward. Are people following that? And then what we really want to do is we start with the actual function body as it was written, with x's and y's in place. And that's what the sort of initial parameter to fold left is. So we take the anonymous function body, and then for each of our bindings, our parameter to argument bindings, we basically want to go and inline that particular call. So we want to say, okay, well, for every x in this body, we want to substitute the value we were given. And now for every y in the body, we substitute the value we were given. And after we've done all that, we now have a tree that has had all of its variables bound, and we're good to go. Yes?
The inline simple function is part of the macro system?
That's something that I wrote, so we're going to get to that. Okay. I'm trying to sort of start high and kind of dig deeper, but that's not something Scala provides, unfortunately.
I wanted to deal with positional parameters here, so I don't care about name parameters and missing parameters.
Yeah, I mean, so I don't think that name parameters are valid for anonymous functions. I might be wrong about that. I mean, I'm pretty sure they're not legal. So we don't have to handle that case because we're not dealing with general methods, just anonymous functions. In fact, literal anonymous functions, like I said. And that's one of the benefits here. We're kind of constraining our domain a little bit. Having to deal with all that would be sort of a nightmare. Geez. All right, you just have to bear with me here. So I'm going to go through sort of the full transformation step again on a tree just to sort of show you what happens. So this is the tree in sort of green up there. That's the actual line the sort of Scala code, and this is the tree below. So this is what we start with. This is the tree. And this is the very first rewrite we do, where we rewrite the anonymous function with apply. So instead of calling, that secret method, now we're just taking the anonymous function and immediately calling it with 6. So we have a very similar tree, but it's a little bit different. It's been sort of flipped around. The very next thing we do is we delete most of the tree. We don't need it anymore. All we need is that function body, which is down there. It's that apply method where we just take this $1 and we find the plus method and we pass it a constant 3. That's all we have to do. And that's what it is. Great. And then finally, like I said, we substitute 6 for x, and now we have it. And this is the tree we end up with. It's much smaller. There's much less going on. And that's it. Great. Shoot. Can people read this? I'm walking this line between making the slides too small and having them actually fit. So anyway, what cleanup is necessary? So the answer is, because we're ripping this body out of a function, we're just tearing it right out and throwing it in our own tree, there's some stuff like owners and parents and things other information in the Scala tree that is no longer valid once we put it in a different context. And so what we end up doing is we reset some of the attributes so that the Scala compiler will recompute those correctly and fix the owners, fix other stuff. To be honest, I don't actually know all the different attributes there are. I just know that if you don't do this, it will cause problems. So now we've shown you how to actually inline method applications. And so the question is that kind of all you can really do? And so the answer, the thing that I think is really interesting that we can do is we can actually generate anonymous classes, or really specifically anonymous instances of classes. And this really looks like C++ templates, which is good or bad depending on where you go to church, I guess. So what's an example of that? So let's say we had this infinite stream trait where we have an infinite stream of numbers. This could be like the Fibonacci sequence. It could be counting up from 0. It could be, like sequence of squares of integers. It could be anything you want. The whole point is it's infinite. It goes on forever. And we might want to do things like get the nth one of these. We might want to get a stream of all of them. We might want to get a vector of the first n. You could imagine a whole bunch of different methods you'd want this to have that are all going to have very similar underlying structure. In other words, like there's only really one way to generate the sequence. So obviously it's a candidate for abstraction, right? We can just have a sort of a general purpose implementation that all these methods will use. And I sort of assert that with this infinite sequence, you can do that pretty easily, right? If you know the sequence's starting state, in other words, the state that will be used to produce the first value, you know how to get from the starting state to the next state, and you know how to get values out of that state, I assert that you can represent pretty much any infinite sequence of numbers, or really anything that way, as long as each term is defined by a relation to its previous terms. Is that clear to everyone what I mean by that? So, for instance, if you wanted to count numbers, the state would be the current number. Getting the number out is trivial, and the way you go from one state to the next is you add 1 to the previous state. That's like a simple example. Fibonacci sequence is the one we'll focus on, which is also very simple, but a little more complicated. But to translate the previous into code, this is really what I mean. I can build you an infinite stream given these 3 functions. Given an initial function, it gives me my first s. I can get from one s to the next, and I can pull values out of s. That's all I need. I can implement all those methods. I can implement nth, I can implement stream, I can implement vector, right? Anything you want. And so here's for the Fibonacci sequence. It's a little more complicated, but still pretty terse, right? I mean, we start with 2 numbers, which are the first 2 numbers in the sequence. It shows us how to sort of shift our window over by 1. So we start with 0 and 1. Next, it'll be 1 and 1. Next, it would be 1 and 2, and so on, right? That's as much context as we need to generate the next Fibonacci number, are the 2 previous ones. And it shows us the rule for generating the next one right there. And finally, how to get a single value out, because we don't want a sequence of tuples, we want a sequence of numbers. People sort of clear on how this is going so far. And we're all Scala programmers. We can probably all imagine implementing those methods given these functions. So imagine if we've done some profiling on this critically important production infinite stream code, and we've decided that it's affected by the inlining problem. In reality, it's not. The code actually will perform fine without inlining, but imagine if we had to inline it. I just think it's an interesting example. So what we're going to do is we're going to use quasi-quotes to build custom infinite stream instances where we actually implement all the methods ourselves using macros. And we can do this once and then inline whichever functions we want. For any infinite stream you care about, we can just use a function call like this, similar to this one. So here's sort of what our template for the nth method would look like with quasi-quotes. I'm using $signs here, right, because I'm interpolating names into this tree. I'll get more into that in a minute. So if you take a moment to let your eyes adjust and try and ignore the $signs, I feel like this is still pretty straightforward, right? I mean, we are generating a tail recursive method called loop, which takes like a counter, I, and takes some state. The state are B and C, two parameters. And basically, if we're at 1, we return a result. At or below 1, we return a result. Otherwise, we keep running incrementing our step forward and looping. And we start out with our initial state using the start function we were given, and then we loop. Great. So just to refresh, these were our anonymous functions we talked about, or very similar to our anonymous functions anyway. There's some slight differences. But if we had those parameters and we inline them here, we'll produce this implementation, which is probably what you'd actually want to write, or very close to it anyway, right? It's like pretty efficient. I mean, there's not a lot of indirection or extra work being done, and you don't see any anonymous functions here. There's still a few problems, though. Like, you see all these tuples everywhere. You probably wouldn't purposely build tuples in your own implementation, or at least I wouldn't. I mean, maybe I'm just a fanatic, but if I don't need to use a tuple, I probably won't. So it's sort of too bad that they ended up in here. And if we had multiple return values on the JVM, then we wouldn't have tuples. We'd actually return two things. It'd be great. Life would be super in that case. How many people here have wished for multiple return values? Okay, yeah, so like a third of people. Yeah, totally, exactly. It would be super nice, and we don't have it, and it stinks. But this is something we can actually fix with an inlining macro. As long as we're inlining into something that we control, we can actually look at the tree and find all the places we're unnecessarily building tuples and then tearing them apart and just get rid of it, right? I mean, we can do anything. This is macro world. We're gods. It's awesome. So, and in principle, this isn't just macros. You could do this with case classes too. I mean, if you're building a case class, a literal case class, just to tear it apart again, you could see that via a macro and just remove it. I mean, why wait for the JVM? Why hope the JVM does it later with escape analysis? Let's just do it ourselves, And so this is something that the inlining macro I wrote does. Specifically, it looks for tuples of any size that are being created and then immediately destructured. And if it sees that, it just literally assigns those vals out of the expression that would have created the tuple. Pretty straightforward. So what are some advantages of this kind of approach? Well, if the inlining problem is a problem, we can win. We can defeat it. We can do the thing that Cliff Click wants, where we can build, where it matters, we can build direct implementations that don't use polymorphism if we don't want to, and then stuff can be safely inlined. A thing Mark Hara brought up that I thought was kind of interesting is that this could actually help you if you are worried about loading classes. I mean, I think SBT might be the only person that cares about this, but when you use all these anonymous functions, those are actually classes you have to load at startup time. And by inlining them, you only have to load one class, the anonymous instance. You don't have to load all these anonymous functions. So this could potentially be an interesting technique there if you find yourself building tons of these little things that could be inlined. It's also fun to second-guess Scala C in the JVM. I mean, who doesn't enjoy doing that sometimes? The thing that I'm sort of psyched about, though, is that I feel like I hit these cases where if I know that if I write a bunch of boilerplate, it'll be faster, and I can actually benchmark it and improve that. And that sucks. I hate that feeling, because then you're straddling this fence where you're either going to write horrible code that performs pretty well, or you're going to write clean generic code that performs slower, and that's just a horrible place to be. And so the nice thing about this is I can secretly write the horrible code, but actually I wrote the nice code. It looks nice. It's as if I was, it's written in a functional style. It's using pure functions, but it's written, it can be inlined into these while loops and this horrible, performance code. And it's just also kind of interesting to extend the language and think about what we can do in this context. So what are the problems? Well, the resetting attributes thing should scare you, because I don't exactly know, the things that will break. I mean, it used to break when I did that. I was recently shown a way to reset attributes that doesn't seem to break anything, so I don't know of any problems, but, who knows until your code fails at compile time for some crazy reason. So that's a little bit nerve-wracking. And like we saw earlier from the question in the audience, you have to be careful what trees you inline. If you inline trees with side effects, the side effect might not happen. It might happen more than once. I mean, you really want to be careful what trees you inline if you're going to do that, which requires education of your users. I mean, we're not used to thinking about these issues in Scala. You have to kind of document and say, look, this is going to look like you're passing a function, but you're actually doing this other thing, so be aware. And finally, I mean, I don't know if, yeah?
Will a debugger choke on this?
No. Or, I mean, it depends on what you mean by choke, but it will definitely not choke. I can tell you that for sure. What do you mean by choke? So here's what I'll tell you is that it will show you, it'll actually show you the positions in your anonymous function without a problem. The place where it's ugly is if there's a bug that isn't, if there's an error, like an exception, that isn't triggered via your anonymous function, but is actually triggered via the quasi-quote, it'll point out the quasi-quote, but it won't tell you, like if your quasi-quote is 10 lines, it won't tell you which of the 10 lines it came from. It'll just say the quasi-quote did it. And the errors will be accurate. I mean, it'll even use the right method names, because here's the thing. If you check the Java bytecode, it's all there. So like using a debugger in Eclipse, You know, those functions will be named, they'll have meaning, but the trick is there's no source code to correspond to them because it's a macro expansion, like you say. So I guess it depends on what you mean by choke, right? I mean, but the thing that I would say is also a potential problem if you all started doing this, if like this entire room was converted to the Church of Scala++ or whatever, and we started doing this, you know, you start to experience what the C++ people call template bloat, right? Because we are going to generate like a full implementation of an interface, and if you do that like 100 times, that's like potentially a lot of bytecode. I mean, if you do it like once or twice, it's really not a big deal in like critical places, but if, you know, doing it 1,000 times is probably a bad call. So that's a potential problem too. This was actually a problem that we used to have. I kept this slide in, but this is actually not an issue anymore because of the way I changed resetting. But it used to be that this was the one case it would break. If you renamed stuff on import and tried to inline it, it wouldn't work. But this actually doesn't happen anymore. I fixed it like literally yesterday and forgot to change this slide. So the other thing that you have to do is, remember how I inserted all those names into the tree? I have to use fresh names because you don't want to have a conflict between the namespace that you've inlined and the namespace that you started with. And the way you avoid that is you use fresh names in your template. So in that quasi-coding I showed you, you wouldn't want to use literal names because you want to make sure that those names have never been used. There's no chance. And the compiler gives you a way to do that. You can ask for new names and it'll give them to you. So instead of X, you might have $X1 or $X13 or, you know, whatever it gives you back that you can be sure is fresh. The nice thing about this is it doesn't really implement your users, it just implements you when you're building these templates. I don't think it's really a big deal, but it's a potential problem. And like I said, this isn't something Scala devs normally do, so it would require some education. This is sort of the end. I don't know how much time I have left. I can actually go show you some of the code or answer questions. I mean, what do you all think would be a good use of this time? I mean, does anyone know how long I have left? I don't actually know. 10 minutes, perfect. Yeah?
I just had a question. What in the development cycle, is there an easy way to like look at these macro expansions? Like, how are you working as you build these things?
So that's a great question. So there is a pretty easy way to do it, which is that Scala provides you with show and show raw as methods in your so actually let's just jump over to the code. Why not? We love it. Great. So remember when I told you about this context object here? Can everyone read this, by the way? Yeah? Okay. So this context object has a whole bunch of handy stuff that I import here. So ct.universe and ct.definitions. So one of the things you get here is you get methods called show and show raw. Show will show you like a pretty version of your tree. So it'll look like Scala code. And show raw shows you that horrible thing with all this stuff. So when I'm working with this, if I'm trying to debug stuff, I can actually print out the tree. And then whenever I call the macro at compile time, it'll generate that tree and show me what it did. So that's probably the primary way. If you're designing this stuff and you're worried about it, I mean, this isn't something I generally have to do when I'm building these. Like, these are pretty obvious. Like, either they compile or they don't, and it'll actually give me a compile error if my quasi-coded tree is wrong. The place where I really had to use that feature a lot was when I was writing this, not verify anonymous function, but this inline cleanup and reset function, because that's the thing that actually does the inlining I showed you, and that actually took a lot of work. Like, Scala definitely does not do that for you. This is me going rogue and doing it myself. So of course you could imagine I created a lot of, you know, fucked up trees along the way, and I had to look at them and understand why they were messed up. Does that answer your question? But as far as like using this, it's actually pretty easy. So let's see, where did I put it? Faster. So imagine I have this blitter. Remember, this was sort of the example I showed you when we started, that blitter, the cliff clicks blitter. So here's like, if we wanted to just write the macro to fix cliff clicks case using the stuff I've already written, this is all you really need to do here. You know, you need to like do some somewhat annoying boilerplate as far as like imports, implement this weird util, or instantiate this weird util class I have. You need to verify that f is anonymous, which I've got this nice little function to do that for you. You generate some fresh names, like I said, because you don't want, you know, name conflicts, basically. And then you just build yourself a little tree here, you know, and you just write Scala code, but you use $ for all the expressions or trees that you want to interpolate here. And then you finally call this inline thing, and the tree would be valid. If you just return tree, it would work. It would just be slow. It wouldn't have done the inlining. So this is the thing you call to actually get it to do all that inlining and removing tuples and all that junk. And now you've got a tree. I mean, this is all it is. So if I publish this thing, which I haven't yet, and you trust me, which maybe you shouldn't, but if you do, it's pretty easy to use this stuff, you know, as long as you're not trying to like extend it yourself. You know, I mean, I don't know if that's like a disclaimer or an enticement. I mean, maybe both. But other questions?
So I haven't verified the behavior of the interpreter itself on this, or the compiler itself on this, but there is a SID1 that actually says that named arguments should be compatible with anonymous functions.
Is that a SIP, or is that like a
SID1 and status is completed.
Well, I would love for someone to. I mean, has anyone here written an anonymous function that takes name parameters?
Yeah, I think Scala uses it for like Fulbright and that kind of stuff.
Huh. Okay. Well, I mean, it's not going to be hard to support. I'll have to look at it. I mean, it'll be annoying, but I mean, it's definitely doable. That's sort of disappointing. I might also even just limit. I mean, honestly, for this feature, it's not even. I don't necessarily even think it's important to support the full range. I mean, really, I'm interested in like function 1, function 2, function 3, function 4, those things, and I don't know if those admit named parameters.
I was going to say, like if you're actually inlining the argument they gave you, it essentially is a named parameter because you're just repeating it every time, and every time it'll, like the parameter will actually recalculate that the entire thing you just gave it over and over and over again. So like, I mean, you don't.
Maybe we should just test it. Who knows? But yeah. There's another question?
I guess. Do you think there's hope for like something like this to be? Would it be worth having in Scala C itself? Like, am I think this would be something I'd want the compiler to do anyways, where appropriate? Or
Yeah, I mean, so I think if I could figure out a way to not have to reset the attributes, I think it's the sort of thing you could totally write a SIP, and it would probably get turned down, but it'd be cool. I think it'd be really great if this feature was in the Scala compiler, because like Spire has this C4 looping syntax that uses this same inlining strategy. I feel like if you want to create new control structures and new syntax that has no overhead, you need to be doing some kind of inlining. Otherwise, you're going to be creating this extra stuff that you don't want. So it would be really great if the macro system or Scala C provided it. I just don't know, like, Scala does not use this strategy for when you use it at inline, they have a whole different set of code that I can't even use to do that. So I think there'd probably need to be some integration work there. I don't really have to be honest, I'm not really trying to get code into Scala C anymore, so I'm a little burned out on that process, but I think it'd be cool if it was,
The inliner per se in Scala C actually does have significant work going into it. Whether Miguel's work is actually going to go mainstream.
Right. I mean, there's definitely work. I guess I just mean, like, I don't think that they want to expose any of that interface. Like, it's doing a whole lot of analysis and stuff that they definitely do not want to expose to macro authors.
Too, right?
Exactly.
In the general case, user code has to be assumed to be impure, so inlining is kind of a
Right, and that's definitely an assumption I'm totally willing in this case to be like, you actually have to pass it the right thing. Sorry, this is about doing the right thing for code that boilerplate you would have, like, because the alternative to this is code gen, which is even worse, right? So I mean, I'm not comparing this against like a perfect world where everything's roses. I'm comparing it against like what our current options are, which is code gen or slowness or praying to the JVM, I guess.
I guess just a couple of comments. Regarding the assumption of purity, I was wondering if that could be a possible reason to have this used wider. Because in the language I was using Idris, the argument to a function, they assume purity there, it's total language, but the argument to a function was being evaluated twice, and normally you're not supposed to see that because it's not supposed to be side effects, and they just blamed it on over-eager inlining. But like normally you shouldn't even be aware of that, but like in the case of the value was expensive to compute, it was kind of being evaluated twice, so it looks for every use of it in the body.
Yeah, I mean, so maybe I should have said this in my slides. It's important. I don't really think these things I'm passing in, I don't think of them as functions in the normal sense. I'm really thinking of them as parameterized ASTs, right? So this isn't something that I think you would want happening randomly to random functions. This is something where I've constructed this particular anonymous function that really represents a parameterized AST, and I want it to be inlined in this templated way. So that's a totally fair point that it could cause overeager evaluation or whatever. The assumption here is that the macro library author has a good template, they know what code they need for it, and the user is going to provide it, and it's going to work. It's not that, it's not something where we're going to try and avoid evaluating if at all possible and be, maximally lazy or whatever. We just punt on that. All right. I think that's it. So, this code is on GitHub. I don't actually have the link here, but feel free to come chat with me about it. I'll try and post it or tweet it. The slides will go online very soon. So tomorrow I'd love to talk about this sort of stuff or have you throw rocks at me or whatever. So thanks.